Alright, section 8.7 is L'Hopital's rule, and it really deals with helping us to find the limits of quotients or functions that are otherwise really difficult for us to find limits of. So we saw these forms 0 over 0 and infinity over infinity in chapter 1 when we were working on limits. We called those indeterminate forms, and if we have limits that take that form, 0 over 0 or infinity over infinity specifically, we can use L'Hopital's rule to find the limit. So it's a really nice, I won't say a trick, but it's a really nice technique that we can use for limits that are either difficult to find algebraically or even can't be evaluated by algebraic manipulation. So L'Hopital's rule is this. So basically what it says is if we have a quotient of functions and we're trying to find the limit as x approaches some value, that limit is equal to the limit of the derivatives, one divided by the other, in a quotient. So what that means is I can take the derivative of the numerator and the derivative of the denominator and find that limit, and it's equal to the original limit. Right? I can do this over and over. So I could take the derivative again. I could take the second derivative over the second derivative, find the limit as x approaches c, or the third, or the fourth even. So it allows us to find limits for these functions that at first glance give us an indeterminate form in a pretty easy way, in a way that's usually a lot easier than the algebraic manipulation method. So we have to, in order to use L'Hopital's rule, we have to have 0 over 0 or infinity over infinity to use it. So there are other indeterminate forms. So there are these. All right. If we get these as our limit, we can't directly use L'Hopital's rule on them until we get them to look like this form. All right. So we have 0 times infinity. We have 1 to the infinite power. We have 0 to the 0 power. We have infinity to the 0 power, and we have infinity minus infinity. So these are all indeterminate forms, but they're forms that we can't apply L'Hopital's rule to unless we get them to look like this. So let's look at some ways that we can get those rewritten. So the first example we'll take a look at is one where we have 0 times infinity. Right? So the function that we're going to look at the limit as x approaches infinity of x times the sine of 1 over x. All right? And if we do this by substitution, we get infinity times the sine of 1 over infinity. So that's very close to the sine of 1 over infinity, which is very close to the sine of 0. So we get infinity times 0. Right? So we have an indeterminate form, but it's not a form that we can use L'Hopital's rule on as it's written here. So let's make this substitution. So I'm going to let u equal 1 over x. Right? And it turns into this. If u is 1 over x, then as x approaches infinity, u is going to approach positive 0. Right? Or it's going to approach 0 from the positive side. So now x becomes 1 over u. Sine of 1 over x becomes sine of u. And now when I look at this, I see that it's really sine u over u. And we know that the limit as u approaches 0 of the sine of u over u is equal to 1. Alright, so that's a technique where we actually didn't even have to use L'Hopital's rule, but we rewrote the limit in terms of this substitution so that we could then evaluate it. Another kind of indeterminate form you might see is infinity minus infinity. Alright, here's an example of that. We have 1 over the natural log of x minus 1 over x minus 1. And when I here if we look here carefully, it's x approaches 1. So I have 1 over the natural log of 1 and 1 over what turns out to be 0. So I have infinity minus infinity. So again, this is an indeterminate form, but not one that I can apply L'Hopital's rule to directly. So I'm going to combine those fractions over a common denominator. Right. So I need an x minus 1 factor in this quotient, and I need a natural log of x factor in this quotient. So I can combine them into the common denominator x minus 1 times natural log of x. And now I get x minus 1 minus natural log of x. Now when I try to solve this limit by substitution, I get 0 over 0, and I can use L'Hopital's rule on this quotient. Alright, so I can take the derivative of the numerator, I can take the derivative of the denominator. Note here that I'll have to use the product rule taking the derivative of that denominator. In this case, I'll have to do it twice in order to find that actual limit. Alright, I'm going to start the next video. We're going to talk about examples of 1 to the infinity, or the power of infinity, 0 to the 0 power, and infinity to the 0 power.